All right, thank you. We're right on time, and we're ready to start the next session in just a minute. Throughout this conference, though, we have a couple of technical challenges and administrative challenges. This conference has always been kind of informal. It's important to be able to hear our various people on their specialized topics, so please be tolerant if we have some administrative mistakes or something's confusing. Now, Dr. Alemu, are you ready to present?
Yeah,
Can you unmute?
pull up my slides and can you hear me?
Yes.
Okay, excellent. Let me come on video. Hi.
Our next speakers are from the Census Bureau. They're lightning talks and they get just 7 minutes each. Yeah, there you are. Okay, are you able to share slides?
Let me just get to it. Can you see the
And we will
slides?
they're coming. Everyone, there will be a Q&A option. Please do post your questions. We will take them when there is a chance, and that might be at the end of the session.
Okay.
Yes, visible. Go right ahead.
All right. Thank you, everyone. My name is Besu Alemu, and I will be presenting collaborative work with Angelica Phillips, Joey Marshall, and Ruth Sarafin from the U.S. Census Bureau Social, Economic, and Housing Statistics Division. As a disclaimer, any views expressed are those of ours and not of the U.S. Census Bureau. This function came out of efforts to improve some of our imputation within the survey, within a certain survey within Census. And one framework we wanted to implement is the multiple imputation by chain equation. I'll briefly describe how this works. This framework, we're able to impute missing values using an iterative variable by variable approach. Each variable is imputed conditionally on all others, one at a time. And then the newly imputed values are available to be used in subsequent imputation model. This cycle repeats over all the variables for a predetermined number of iterations. And this framework is flexible in that it's able to handle mixed data types, meaning we could use categorical as well as continuous variables. We could work with those. Why did we go from the existing Python packages within mice to my census is the name of our package. There are certain limitations that exist within these packages. I'll outline 4 of the main ones we found. They tend to treat all predictors as continuous despite other specifications. They would impute predictive probabilities rather than actual realistic values, especially within multinomial models, using all regressors to impute for each variable when we don't really want to do that. And then they're a black box in the sense of we're unable to access the inner workings of these functions. With our package, My Census, we're able to overcome some of these limitations. We could customize the imputation model based on the variable type, appropriately handle predictive probabilities for categorical values in nonlinear models, allow specification of imputation condition and regressors for each variable, and record noisy output in a log file. There's certain dependencies for My Census, namely NumPy, Pandas, and scikit-learn, SciPy, and OS. My Census has 7 arguments for which are required: input data name, the log file where we want to record everything, the number of iterations we want to perform, and whether we want to shuffle variables within each iteration, Three optional arguments, two of which we found useful. We're able to set conditions, meaning we could impute X if, say, Y equals to 1. We could set predictors, the default being all columns are used as predictors, but we could set predictors for each variable and seed for replicability. And then this all returns a pandas data frame with the missing values imputed. The setup for my census is as follows. For each column in the data frame, it identifies whether missing data exists in the imported data frame column. It initializes all missing values with the mean, numeric, or mode for categorical columns. And then it identifies a type of imputation model based on the column type. For numeric columns, it's linear regression. For categorical, it's either logistic or multinomial logistic regression. And then it specifies, as I mentioned, the predictor dictionary. And then it converts the categorical predictors into a binary format using one-hot encoding. So the imputation process itself has three pieces: fitting the model, missing data imputation, and wrapping up. In fitting the model, it sets the missing values to null in the first iteration. Then it fits using non-missing data, and then it generates predicted values based from the fitted model. And in the imputation stage for numeric columns, it conducts predictive mean matching to randomly select a non-missing value from the k nearest neighbors closest to the predicted value. And then for categorical, using the predicted probabilities, where it imputes categoric by conducting a draw from the weighted by the predicted probabilities. In wrapping up, updates the data frame with the imputed values, logs the relevant information, and continues the entire process for a preset number of iterations. And then at this stage, it also used the newly imputed values as inputs in subsequent models. For the next steps, we want to incorporate additional model types. Namely, we're interested in non-parametric methods such as XGBoost. We want to expand the customizability of the function, allowing for mid-imputation edits and multiple implicates. We want to incorporate error and exception handling as well as stress tests before putting into production. That's all I have. If you have comments, please send to the email here. Thank you.
Super. We have time for a question. Do you see the question in the chat about imputation of multinomial outcomes?
I don't see it. Sorry.
It's in the Q&A box. I'm going to read it. It looks like imputation of multinomial outcomes with one-hot encoding will result in probabilities not summing up to 1. Why not use an actual multinomial instead?
Okay. I think it's a matter of the dependencies we're using. It might be, I'll have to go back and look, but if you could contact me. We're using SciPy, scikit-learn, and I think one of the things we needed to do in order to use that dependency is we had to convert the multinomials into, using one-hot encoding into binary. So I would like to hear more back about that. Thank you.
We have a question from Aji Diagne. Please put that question in the chat box. I don't know if I can allow you to just speak. We'll address it at the end. Thank you, Dr. Alemu. And we will probably have time for more questions at the end. Because these are lightning talks, I want to go quickly. Ray Ellis, are you ready to present? Can you try to share your slides?
I am. Let me see if we can get the slides to work. Okay. Are you seeing my slides?
They look good. And all speakers just answer questions in the Q&A if you see them. Yes, go ahead.
Okay, thank you so much. I appreciate being here. I'm excited to share a little bit of work that I've been working on with Sanchez Rivera about solving some of our challenges that we have in using Paradata. And I'm just going to jump right in because we don't have a whole lot of time. So Paradata broadly is a really rich source of data for analysis, and we use all kinds of modes of Paradata, but here we're going to focus on internet Paradata. Internet Paradata is basically a record of all of the actions that happen when someone is using an internet instrument. Because it's part of the instrument as an artifact, it's actually inexpensive to collect, and it's a rich source of information. It provides us information that can use to be target problem questions or improve surveys. Now, it's wonderful data, and we're increasingly using it, but it is large, complex, unstructured data, and we often have very short windows of time to develop programs. You need specialized skills. Your analysts need specialized skills to be able to deal with Paradata because it's in an unstructured and uncommon format. And our programming time, often we have this issue where because of Title 13 and because of policy protections, we can't really get access to the data until we're in that process of analyzing. And we might need different programming tools, even if we've done a survey in Paradata before. Small changes in the survey can result in large changes in the Paradata. So what we really want to do is take that window of time, that short window of time that we have for training analysts and programming, and expand it out by having a source of Paradata that imitates the structure enough to teach and to actually facilitate programming. And so what we're really looking at is this idea of using keyed test Paradata. Now, keyed test Paradata is generated every time a survey is developed for the internet, and it is developed to test the survey before it goes out in the field to make sure it's working properly. And so we generate hundreds of synthetic records that are essentially subject matter experts going through and keying through the instrument and looking for issues, looking for bugs, looking for response category problems, looking at those behaviors that might be problem behaviors and looking at what they do to the instrument. So what they do is basically develop data that imitates the structure of the data, the Paradata. However, it's not going to be exactly. The motivations for subject matter experts and people who take the instrument are going to be very different. So we expect differences in the data. But what we really hope for is that the data has the kind of structure that we need to be able to program. So what we really wanted to do is test this out, test drive it. So we wanted to really look and see if the Paradata can help us extend that time for developing programs. And so we wanted to look at the structure and the content of that data to see if we can really use this data to save us time on programming and to develop teaching programs for training analysts. So for this purpose, what we did is we took and we programmed the data on keyed test data. We programmed our program, and then we tested it on real data. And we sliced it for the information we're going to show you today. We sliced it to one question. We chose the Hispanic origin question because it is a question that we know from research has a lot of activity, has a lot of movement and breakoffs and those kinds of things that we really want to see. So we knew it would be a good example. And we know that it's also a question that's very carefully tested by analysts. So we programmed in the 2024 ACS test data, and then we tried that programming out on the 2022 ACS Paradata. Now, the good news is our program worked. We got through the program, it worked the way we needed. And so as a source, the data works pretty well. Now, what we want to really pay attention to here is that the data, because the motivations are different between those people and real people, you're not going to get the categories that are same. So you can see in the key test Paradata, we have sort of all of those categories of time covered, but the main times are very different. So if you wanted to make a decision on how you're going to bucket your data and categorize it, you probably don't want to use the key test Paradata. You want to wait that until you have real data, but you can do your basic programming. Now, here's another example of a table that, or a figure that we built with the data. And in the case of the key test Paradata, we saw 2 categories of error messages, but in the real data, we found 3. The good news is our program was open-ended enough that it found this category. We just didn't know how to prepare for it in advance, right? So that meant maybe changing tables or figures or things in downstream, but largely the data was in a good enough structure. So here's the sort of the key takeaways here. In terms of whether the data measures looks like structure and content, yes, the structure is the way we need. We can build a program on it. The data looks the way we expect it to. The content does not generally mirror it. Now, this isn't a big surprise because the people who are programming are different than people who are actually answering, who are testing are different. And it's not a big deal for us because we do get enough complexity in the data to be able to train on, and we get enough complexity in that structure to be able to write programs. So it is efficient to save us time and give us a little bit of time, but it does mean that we will have to make some adjustments to our program on the back end once we get real data. So we have great advantages here in preparing for data wrangling, coding for visualizations, reducing that analysis time in production, and for being able to train new analysts and teach them. There are some limitations. We don't want to use this data because it doesn't mimic real worlds to confirm research questions or to build categories. And because there are big sample size differences, hundreds of cases versus thousands, you have to think about that when you're building graphics because they're going to look very different when you get that full population. But overall, this is a really good tool in our toolbox to help us extend our time that we need and allow us to have extra programming time and more importantly, train more analysts so have them ready when the data is available. And there's our contact information, and thank you very much.
Great. I'll watch for questions just a moment here. Not seeing any yet. Thanks very much, Dr. Ellis. Anyone feel free to pose questions in the Q&A for Dr. Ellis. Our next speaker is Tucker McElroy.
Okay, here I am.
Can you share slides?
Yeah, I'm on it. Let's see here.
Very good. Oh, that worked.
Okay, that better?
It's good. Go ahead.
All right. Yes, thank you. This is work in progress, and it's an algorithmic talk. So the title is Recursive Computation via an Information Sieve. This is joint work with my colleague, Redouane Betrouni. And standard disclaimer. Okay, so jumping right into it, the outline, I'll be talking about a little bit about the information sieve, that idea, the recursive algorithm that we developed, and some of the applications. It's more just an overview of their current work in progress. So the context here, we're looking at multivariate time series, usually, maybe 4 or 5 time series at this point. So it's not a massively multivariate situation. And we want to be able to look at time series exhibiting extreme values like additive outliers, level shifts, temporary change, possibly missing values, which could be a different arrangement of missingness for each time series. We want to be able to look at possible changing of sampling frequency, like a time series that was monthly for a while and suddenly it changes to quarterly, or vice versa. And we want to be able to deal with sampling error, which has a kind of a heteroscedastic structure. And the kind of things we want to be able to do are likelihood evaluation, imputing missing values, maybe doing some forecasting, backcasting, or even doing signal extraction like seasonal adjustment, for example. So the main contribution is an extension of the algorithm that's already available in a R package called HA-Signum. HA-Signum is a little bit more focused on just time series are a bit more regular. They just have the ragged edge. But the extensions that we have in mind and that this new algorithm allows for, those extensions would be the handling the extremes, changing sampling frequency, and adding sampling error. And I'll just note, this is not state space stuff, okay? So you can handle non-Markovian structures. The algorithms are kind of more the feel of Durbin-Levinson rather than Kalman filter. Okay, so the basic assumptions is you got n-variate time series X, and there's a deterministic linear combination H that can basically handle heteroscedasticity. The Z process is different stationary, so it could be like co-integrated VAR, or you could have component Riemann models. That part's pretty flexible. And what you're going to observe is just chunks of that X process. Maybe there'll be some gaps. So as you're going along in time, perhaps you don't get any new information. This F is sort of the symbol have for the information you have up to a certain time. But if you do get new information, it's a linear combination C of everything up to that time T. Okay, so this device allows me to handle all kinds of things like mixed frequency data and arbitrary patterns and missing values and things of that sort. Okay, and then what we're trying to do is, well, essentially they're Gaussian conditional expectations, so best linear predictors, and P is the notation for that, and then V is the mean squared error. So it's just a little bit of notation we have for that, because I'm going to show formulas in a couple slides. So one thing we do have available already from the efficient Durbin-Levinson algorithm is the one-step ahead predictors for different stationary time series. And L is this matrix, which I'm using to denote that one-step ahead predictor based on past T observations. And we also have a mean squared error for that, which we can efficiently compute. So the main result is here. If you want to update your current estimates of this Z process, with new information and at the new time point, here it is. You can see how the previous estimate, the one-step ahead predictors are involved, and then you've got another modification here. So all the pieces from the previous iteration of the algorithm are employed, along with the heteroscedastic part H and the information sieve portion C. Okay, and it's a bit much to digest, but that's the gist of the result, which we're in the process of implementing. Here's also the update for the MSE. Okay, a little bit simpler formula. Okay, so what are the applications of this that we have in mind? Well, doing likelihood calculations and doing the casting. And we might look at processes with sampling error. So here, for example, X could be like a population process U, which could be different stationary, plus a sampling error term, which would look like maybe something like a autoregression, and then you've got a time varying component S, which is the square root of the sampling variances. So that's an application that comes up quite a bit in time series surveys. Or maybe we have a changing sampling frequency, like halfway through the series, it goes from monthly to quarterly. This can be described through appropriate choice of the information sieve C. Okay, so that's one possible application handling that. And then finally, looking at more general types of extreme values. Right now, HA-Signum can handle additive outliers, which is just a very simple kind of extreme, but we want to be able to do level shifts and temporary changes and ramps and all kinds of other things. So those can also be handled through appropriate choice of the information sieve. Well, I kind of blasted through that, but here's the future work. This is ongoing. So the goal is to implement this algorithm in HA-Signum, expanding on the current functionality. I want to do an RCPP version to really speed things up. And then Redouane is going to help me with the GUI and, of course, doing some testing. There's my contact email, so please reach out if you have any questions or you're interested in this research. And then the repo is called SIGX. That's the current version of HASignum. Okay. Should I stop sharing?
All good. Yes, that's fine. We can watch a moment for any questions coming in. Oh, there is a question. Do you see it?
Savitsky. Oh yeah, Terrence. Hey. Joint nonlinearity. Not sure I understand the question. Yeah, so there's time series dependence, which is serial coming in time. And some of that's going to be through this heteroscedastic structure. And then there's cross series dependence as well. Through we might have like a multivariate time series model, like a vector autoregression, so you can have cross-sectional dependence as well. So the dependence structures can be fairly flexible. It goes a bit beyond like their current version. I'll follow up more with Terrence offline. Good.
Yeah, go ahead.
All right. Thank you so much. Thanks everyone for the previous presentations. And thanks, Peter, for hosting this first GASP session panel. I'm going to show something today about similar to low response scores, which are used to understand unit non-response. This is actually going to focus instead on item non-response and coming up with the score for that. So here is a randomly generated simulated survey with 4 respondents and 4 items. There is a 100% self-response rate, and race has a 75% response rate, and Hispanic origin has a 50% item response rate. So the method in this demonstration is going to map notions of correct and incorrect to a general score for each respondent, somewhat similar to ability. Here, correct corresponds to the item has a response. Incorrect means it does not have a response. Each item will have a implicit difficulty score that is common to all the respondents. And if this sounds familiar to you, you participated in such scoring if you ever took the ACT, SAT, GRE, or any other standardized test. So again, the task here is to identify places that are prone to low item response. And the way that I'm going to get to this is with item response theory. So I'm going to show proof of concept for a method to identify such places that are prone to low item response, and focus on scores derived from specific respondents and the sum of their activity on the census survey. So item response theory presumes that everyone has a latent unobservable trait that can be measured by having respondents reveal information about that trait through choice. The choice is either some sort of multiple choice question that can be graded as correct or incorrect, or some sort of ranked options like on a Likert scale. An item response model will then estimate the most likely value of the unobservable latent trait given choices made across all respondents. In this application, the latent unobservable trait is akin to compliance in a sense of civic duty. So if one is more compliant or more willing to engage in something like civic duty, the more likely we expect to see item response occur. Similarly, item non-response to not occur. So here's the general methodology. We know respondent location even before an individual attempts to complete the survey. Given that the individual has initiated a response, recode all responses with a 1 and all non-responses with 0, and then estimate compliance for each respondent. Pair that estimate with the a priori location of the individual, and then either plot those estimates or create averages by geography of your choice. So let's go back to our previous example. We had particular items that had non-response. I put red X's there. So for the data pre-processing step, we just convert the red X's to zeros or non-response to zeros as the notion of incorrect, and then keep the other ones as ones, even if they are not the true values. Remember, this is an assessment of non-response, not necessarily the ability to do a correct response, because we don't have a notion of correct yet. So here's a simulation exercise that's going to demonstrate this proof of concept. There are many R packages that can estimate IRT models. MIRT is just one of them. So steps 1 to 3 from the methodology slide earlier are the same steps as 2 to 4 here in this simulation exercise. So let's look at some outcomes. So here are respondent level estimates in the DMV area from my simulation. I want to emphasize this is not real data. This is all contrived data, just showing that fitting the model, developing the scores and estimates in something that looks similar to a census survey is feasible. So in this plot, blue and purple dots correspond to the lowest 2 quartiles of compliance. Orange and yellow correspond to the highest 2 quartiles of compliance. For tracked averages, not everyone has a tract, because in my exercise, I wasn't able to sample at least one person inside of every single tract. At the state level, this is what it would look like. These are averages for estimated compliance scores by state from the simulation exercise. So again, remember, this isn't real data, but if it was, states like Wyoming, Louisiana, Illinois, Tennessee show a lower propensity for item response in other states like California, Ohio, West Virginia, or Virginia. This example drills down to county level estimates, and one can of course refine this to whatever geography one chooses. The next steps for this are to incorporate real data. I'm going to generate these compliance scores by response mode. The low response scores, remember, are specifically interested in non-response, unit non-response through mail. These scores will be easy to generate by any response mode that we're interested in. And I'm also going to generate estimates for compliance that control for spatial correlation using Gaussian process item response theory. So another best linear predictor. So if you have any questions or thoughts about how this model can be used in your work or the estimates I'm describing, I'd love to know about them and talk about them more. Please send me an email. Thank you very much for your attention, and I look forward to hearing your thoughts.
Very good. We'll keep an eye open for questions or comments. We've got another couple of minutes. Let me just invite any of the panelists to add an additional thought or pose a question to one another. Just go ahead and speak up, and we'll keep an eye open for questions from the audience.
We need to chat, Ryan. I would love to hear more about your work. But I have a question for you. So not all questions are created equal, as in we have questions that we sort of are privacy type questions or sensitive type questions. And some of the work I'm doing looks at people who sort of miss answers randomly versus sort of systematically, right? So you have people who might only not answer private sensitive questions, or you might have people who answer fine until they get to the end of the survey and then they get tired, right? So do you have thoughts about weighting questions in terms of those kinds of different challenges?
Yes, that's a great question. That's another step that I want to take this in. This started with this idea of how can we systematically find, for example, areas of the U.S. where it seems like maybe Hispanic populations are not responding at the same rates as others. The examples you gave are also are excellent. Differential item response or differential item functioning is something that we look at, which is there's this assumption that everyone's being tested on the same scale. Kind of like when we all go take the SAT or LSAT or whatever, they're assuming that everyone has this same measurable scale that's in common. And ways that item response theory looks for these, if that's potentially not true, is with these differential item tests. And so that is an eventual goal, and actually what I thought was the what made this method seem very appealing and useful.
Thank you.
I have a question for Tucker. Since you also had best linear prediction in your presentation, when might your model be able to accommodate best linear unbiased prediction? Is that something that you're not really concerned about with the applications at hand?
To whom goes that question?
That was for Tucker McElroy.
Tucker, go ahead and unmute if you can.
I can also email him that question later.
Anybody else, go right ahead with any question. And if we don't have any more, I'll wait just a moment. Tucker, go ahead. It's true that we cannot perfectly tell, as just asked in the Q&A, who can hear us and what's happening, but that's just the way it is. Okay, seeing no other questions, I'm going to hand on to the next chair.